Thank you. Alright, capacitance and capacitors. Got that? Yep. Not yet. Do you know these words? No. Explain.
No? Monica did the presentation.
Oh, dang, that's embarrassing.
I don't remember your presentation.
The kind of photo.
Yes, Andrew.
You remember?
Yeah,
what asked questions was.
Sorry, the next one was also really.
I'd be offended. Okay. So consider the following. Very simple circuit here. Very, very simple actually. What you have is a cell and two metal plates. And these metal plates are quite close together, but they don't touch. And something happens here actually. Okay, so at the very beginning, before it's on, ugh, ugly. Let's put a switch. Before it's on, what's the charge here?
0.
Yeah, the charge will be 0.
Yes.
Okay, then you close the switch. Ooh. And the current starts to flow. And in fact, what you'll notice that happens is that this plate starts to have a positive charge and this plate starts to become negatively charged. So at the very beginning it was no charge. That means the positives and the negatives cancel at the beginning, no charge. But then when you turn the switch on, they separate, and then all of a sudden you'll find that all the positives have become here and all the negatives have landed here. And so this one will have a positive charge and this side will have a negative charge. But what's most interesting is if you turn this off, that's it. For a moment, very good. For a moment, you still get a current. Because, think about it, if this is positive and this is negative, they won't just sit here and do nothing. What would happen when you have positive and negative? They'll attract. So this causes the electrons to move left or right?
Right.
Left. If the electrons move left, then the current continues to the right still. So capacitors are a way to store charge temporarily, and then the charge is released. Yes, are you cold?
Yeah.
Windows closed. Okay. So, what definition did you give for a capacitor in your presentation? Yep, sounds fine to me. So a capacitor, also called a condenser, but nobody says that, is an electronic device that stores electrical energy. Very simple. And in fact, it's a very simple device. It's just two pieces of metal close together. That's all it is. And the symbol for a capacitor is this. That's the symbol for a capacitor. Got that? Yeah?
Yes.
So we need some way to measure how big our capacitor is. Can our capacitor hold a lot of charge? Maybe it can only hold a little charge. So we need a new unit to measure something that we call capacitance. So capacitance is the ability to hold a charge, such as a capacitor, and the unit is the farad. Mathematically, capacitance is charge divided by voltage.
Yes.
So each coulomb per volt, that's one unit of capacitance called a farad. So in other words, 1 farad is 1 coulomb of charge held for every volt that you have. Okay, so you need to write this definition down. Can you write this down, Sean? Got that, Jerry?
No.
Yeah. Yep. Continue.
Yeah.
Okay, continuing. Yep. So here's an example of why capacitor is useful. Here's an old example. Capacitor can hold the charge and then suddenly release the charge at once. So here's one example of using a capacitor to make a bright, short flash of a camera. What is another example of using a capacitor? Charging what though?
Power bank.
No, they're not actually capacitors, because the key thing about a capacitor is it holds a charge for a short time. When you charge a power bank, there's a chemical process going on. Capacitors just literally holding the charge, waiting to release it.
The light polishing.
Battery.
No. You need to be thinking of something that releases energy quickly for a short time. Huh? Flash, yeah. What else? Another example.
Radio.
Projector.
Radio.
No. This isn't it. Capacitor.
Radio.
Huh? Radio? Maybe, but give me something that gives a lot of energy in a short time. Electrical. No, but you can set the microwave for like an hour. That's not a short time. No. Well, no. Electric gun is getting closer. Electric gun would be one example. A stun gun,
Phone charger. Sometimes you turn it off.
This.
What?
Yes. Yeah. Obviously, this is used as a capacitor, and in fact, you can actually hear the capacitor building the charge. Yes, you can hear it. Yeah. So this is an example of capacitor. Now, on to some formulas for capacitors. Before that, a short little question here. A flash camera has a capacitor in it. When you press the button, it charges until you get the flash. The capacitance is 1500 microfarads, and the voltage is 380 volts. I don't know why I said the voltage is so high in the camera. I don't know what I was thinking. But anyways, it's really good camera. The voltage is 380 volts, and the capacitance is of 1500 microfarads. What's the charge held, please? Multiply, yeah. So what did you get, please? 0.57.
0.57.
Now remember, it's microfarads. Did you put in the 10 to the minus 6?
Yeah.
So you got 570.
0.57.
0.
0.57.
Which, you're not saying the unit.
Yeah.
Okay.
Coulomb.
This times micro.
Mine are 6.
Yeah, micro.
Oh.
Monica, what's the full answer here?
Thank you.
0.57
Coulomb.
coulombs. Okay. That's how much charge is held. Simple little formula here. Yeah. C equals Q over V. So here the voltage was 380 volts and the capacitance here is 1500 microfarads. So the charge it can hold here is 0.57 coulombs. Happy with that? Yep. Okay. Yeah.
For the distribution, how come usually?
I think that's just a movie thing. I don't really think they have to do that.
Yeah.
They start
Where have you seen them do this?
Movie.
I think
really like, yeah.
okay, I don't know.
Okay, if they do that, if those two things touch each other, what's happening? They can't put it down.
Yeah, I know. So I don't really know what's happening when they do that. I'm not even sure that they do that. I'll have to look it up. I just know I wouldn't be doing that.
You will.
No, I wouldn't be doing that. Do I look like a doctor? Okay, so now, how do capacitors combine? So the first one is, if the capacitors are in parallel, like this, and we want to replace this with just one capacitor, and this is C1 and this is C2, then here, the total capacitance you actually add it straight. So this is C1 plus C2. So that's our first rule, if you can write that down, for parallel. Yeah. Now, you might be wondering, well, why is it as simple as this? Why isn't it like 1 over C? Something like that. Well, to explain, here, if this has a minus Q1 and this has a Q1, when the current is off, these get pulled together and it causes a current here that carries a charge of Q1 to flow. And likewise here, if this is minus Q2 and this is Q2, when the current is off, they'll pull together and it causes a flow here, and this will be a flow of Q2. So these, basically because I equals I1 plus I2, when they're in parallel, it's Q1 plus Q2 is what you get out here. Yeah? Okay. Also, please remember that the voltage is equal. So here, the V1 here will be equal to the V2 here. Yeah. Now that also gives you another clue, because they're in parallel. We said voltage is the same in parallel. Yeah? No, I didn't. Yeah? Yes. Okay. Next. Oh yeah, so that means in this picture here, this voltage is what? The same as V1 and V2. Why? Because they're in parallel, and that's how voltage behaves. Okay. And you know this as well, that the charge adds. You add the charge together. But you kind of knew that because it's like the current. Now the next one, series, is actually a bit unusual. Can I scroll down? So, what if you had something like this? You had one capacitor here, one capacitor here, and we want to know what can this be replaced by. Well, it might seem a bit odd, but the formula is actually this way. 1 over C1 plus 1 over C2. Yeah? Now, what's happening here? If this one is minus Q1, this one will be plus Q1. This one will be minus Q... Oh, sorry, what am I saying? 1 minus Q2, and this one here will be plus Q2. Right? But everything here must actually be equal, because imagine this Q1, let me write that a little bit neater. Imagine this Q1 was much bigger than this minus Q2, then they wouldn't be balanced and the current would try to flow. So if the Q1 was bigger, let's say this was a positive and this was a negative, then they'd want to move together, and which one would win? The Q1 would win. Yeah? So the Q2 would get pulled over to it. If it was the other way around, then the Q1 would get pulled over to this. So to be balanced, to be in equilibrium, it must be that Q1 equals Q2. So now we get this picture. Minus Q1, Q1, minus Q1, Q1. But effectively, these middle ones here we don't care about because they can cancel. So this picture is kind of the same picture as this. In other words, quite strangely, Q1, the charge held here, must equal Q2, which is the charge held here, which also must equal the total charge. Now this might seem really strange if you think about it. You know, if I said this has Q1 and this has Q2, I put them in series, then I know this one must equal this one. Okay, fine. So this is Q1 and this is Q1. I put them together and in total I don't have 2 Q1, I just still have Q1. Now that might seem very strange, but what's happening is in between the capacitors there's this sort of cancelling effect that's happening, meaning we only really care about the ends of the capacitors, not what's happening in between them. And you can prove this. It's a little bit messy to prove. I used to prove it in class, but it's a bit complicated and messy. You can take my word for it anyways, that the charges are equal this, and that the capacitors combine according to this formula. Remember that voltage adds, that's the key thing here. You can kind of see this formula. It's actually, okay, it's not too difficult to prove. If you're happy with the idea that the charge must be equal, then the formula is straightforward to prove. I'll just show it to you quite quickly. If you're happy that I say Q1 must equal Q2 must equal the total, and you have the formula C equals Q over V, then you have here V1,
C1.
well actually before I get to that, just hold that there. You know that V1 plus V2 must equal the total V, because they're in series, and you have the formula C equals Q over V, so V equals Q over C. So then this is Q1 over C1 plus Q2 over C2 equals total Q over total C. But if you're happy that the charges must be equal to be in equilibrium, then these must all be equal, and we can kind of see this formula now. Yeah, so I mean, you know, it's a bit, I don't particularly like this proof because you need to first be happy with this. But anyways, they're not too difficult to prove. These are the 6 formulas for the capacitors. If you can please make sure you have these written down carefully. You have these? We'll look at some examples in a moment. Continue? Yes? Yes, you have this? Continuing? No. Who's writing? Sean, you're writing, yeah? Chrissy writing now? Are we just waiting for Sean?
Yes, okay.
Okay, what? Don't wait for you? Continue?
Yes.
Yeah, okay. Okay. Relax, it's not so bad. We'll do this one together. We'll do this one step by step. So the first thing is we'll draw. A 100 millifarad is connected to 200 millifarad. They are charged by using a 10 volt battery. A, they're connected in parallel. Draw this circuit. Okay, draw this for me, please. I'll give you the answer in 30 seconds. Yeah? Okay, let's draw this. So, they're in parallel. So, it's like this. Parallel. 10 volt, 100 milli, 200 milli. Part A. Okay, B. What is the total capacitance? Okay, total capacitance, what formula do I use? Yeah, so what would it be here? What's the answer here? 300 millifarads. Okay, C. What is the charge on each capacitor? Are they the same or are they different? Different. Because I told you it's different. Okay, Q1, we have the formula C equals Q over V. So Q is C1 V1, which is 0.1 multiplied by, what's the voltage? 10. 1 coulomb. And Q2 equals C2V2, which is 0.2 times 10, which is 2 coulombs. Okay, D. Oh, not D, sorry, these are not letters A, B, C, D. It should be 1, 2, 3, 4. 1, 2, 3, 4. Not that it matters too much. Okay, 4. What is the charge in total? What's the total charge here? What's the formula? Plus. So here it's 3 coulombs. Part 5. What is the voltage on each capacitor? That's funny, I should have asked you that earlier. It's 10. But if you want, you can use this formula to check the answer. V1 equals Q1 over C1, which will be 1 over... Where's my C1? There it is. 0.1. 10. And then V2 equals Q2 over C2, which is 2 over 0.2, which is also a 10. Yeah? Okay. Got that okay? What about it? It's ugly, I know. Don't make fun of it. Oh my goodness. That changes everything! Changes nothing. Okay. Don't look shocked. Nothing has changed. Don't worry. Okay? Correct. Correct. I'll keep an eye out for that when I'm grading your exam. Make sure you don't make that mistake. I'll be very disappointed if you do now. Okay, did you draw that? That's done? Do you have that?
Yes.
So I want you to try by yourself. The second half is just if they're in series. Okay? So I'll give you a minute and then I'll check your answers. Okay. Okay, let's have a look at the answers together now. Right, what is the total capacitance? Did anyone get it? 1 over 15? What unit? Bananas? 1 over 15 farads. Yeah, okay. And the charge on each capacitor is the same, isn't it? And what is that? 2 over 3 coulombs. And 2 over 3 coulombs. And what's the total charge? 2 over 3 coulombs. And finally, the voltage will be, what's it going to be? Something like 6.67 and 3.33 volts, is it? What's the voltage on each at the end? Is it like 6.67 and 3.33? Yeah, because they need to add up to 10. What's wrong, Andrew? Did you get this or not? Andrew?
The first one?
Yeah, what's the first voltage? You don't know?
Because it is different voltage for each capacitor.
Yeah, so tell me what the voltage for each is. I mean, how can you? You have your formula, C equals Q over V.
Yes.
Do you know the C?
I know the C.
Do you know the Q?
Yes, I know the C.
So, tell me the V. Q. Did you get the voltage?
Oh.
Okay. What part are you on? Okay. Do you need me to do this one?
Yes, please.
Yes? You want me to do this one? Okay. So, the first one, I don't need to draw it. Well, okay, I'll draw it roughly, but in series is like this, yeah?
Yeah.
100 millifarads, 200 millifarads. 1 over C equals 1 over 100 millis. These are in millis. Plus 1 over 200. Okay, what's that now? That's 3 over 200. So the capacitance is 200 over 3 millifarads. So the capacitance is, what's that? Is it? Yeah, 66.67 millifarads. Okay, what's the next part I ask you for? Part 3.
Q1 and 2.
What's the charge? Yeah, we know that Q1 equals Q2, and the formula for Q is CV. Ah, yeah. So not as easy now, because what do you use for the C?
1 over 16. Oh, okay. 66.6.
Well, there's two problems, yeah. If you're using the CV, then the only V you know is the total V.
Total V.
So you should use here total C. So we don't know that they're equal. But then we remember, wait a second, if I know what the total is, I actually know what each of them are, because I know that the Q equals Q1 equals Q2. So I can actually know all three at once by calculating the total. So the total voltage is 10, and the total capacitance is 66.67 times 10 to the minus 3. That's 10 to the minus 2. So what's that? 0.667 coulombs. And that's also the answer for part 4. Part 5 is what's the voltage on each of them. V1 equals, V2 equals, yeah, Q1 over C1 and Q2 over C2. 0.667 over 0.1, 0.667 over 0.2. So this is 6.67 volts, and this is 3.33 volts. And that's good, because it means that the total
10.
is 10, which is what it should be. It should be 10. Yeah? Did you get this?
Yeah.
Okay, good. Continue. I see people writing, so I'll write them. I see many people writing. Yeah. Continue? No? Okay, so again, just like in the last lesson, I did not have any time to put these onto a worksheet to print out. Let me just check if these questions are okay. Ah yeah, these are okay. So if you can try these 4. Okay, I still think there's a little bit of time, isn't there? Yeah, there's 5 minutes. Can you try these for 5 minutes so I can leave them open?
Draw?
Yeah, you can try these for 5 minutes. I don't think I asked you to draw, do I? You should though.
I mean, you just draw that.
Did I say draw? I think I did. Nobody heard that. Maybe you're having the same problem as you did during Monica's presentation. Could be that.